So, period 3, get excited to watch math using the internet. It's amazing. Learn math using the internet. It's amazing. So goal today is to kind of just catch up since we've had 50 million snow days, and they're not really going to move the date of your AP test. So we're going to finish up some polar stuff that we didn't do because of the half day on Friday, and then also start a little bit of polar related calculus. So I think we left off last class trying to convert or reviewing how to convert polar equations into rectangular equations. So we had r equals 5 sine theta. And we had basically 4 fancy conversion tools. They were that x equals r cosine theta, y equals r sine theta, that x squared plus y squared is equal to r squared, and that tan theta is y over x. All things that can be just shown by drawing a little triangle, if you forget those formulas. So there are 2 things that people like to do here. For me, I know that x squared plus y squared equals r squared, so I like having r squared. So you can create r squared with one of 2 methods. You could actually take both sides and square them. And then you just get r squared, just duh, because that was the goal. And then you get 25 sine squared theta. Left side works out all nice and pretty, which we kind of knew was going to happen anyway. It's just x squared plus y squared. Right side does not work out quite so pretty because none of those things are sort of readily apparent here. So right side, kind of a mess. So option 2 for getting the left side to turn into r squared is to actually physically multiply both sides by r. So we get an r squared, and then this time we get a 5r sine theta. And the left side still works out just as pretty as it did before. And the right side actually works out a little nicer because r sine theta just is y. So this thing is just 5y. And we're basically done. I got rid of the r's, I got rid of the thetas. It's maybe not quite so apparent, maybe to some of you, what this actual equation would graph as. It's maybe more obvious if we mess around a little bit. Subtract a y. Well, I guess this is still equal to something. And then we could possibly, if we wanted to, add 5 halves squared to both sides. And then if we just factor this expression, we're looking for 2 numbers that multiply together to be 5 halves squared and add up together to be a whole 5. That's probably 5 halves and 5 halves. And then this is just 25 fourths. And now we just have a circle. I can spell circle. The center of that circle would be 0, 2.5. The radius of the circle is just the square root of that, which is also 2.5. So you just have a circle with a radius of 2.5 and a shift of 2.5. And the diameter of that circle would be 5. You hopefully know that just r equals number cosine theta, r equals number sine theta is just a circle, and that's its diameter. Sine functions tend to have vertical symmetry. Cosine functions tend to have horizontal symmetry. This is hopefully like the least surprising thing ever. Cool.
Cool.
Okay, so Mr. Rose, anything to add?
Nope.
Yay. Okay, so successfully converted, and we know a bunch of formulas. The other thing I want to go over is graphing, and for that we get to travel back in time to like 1986 when people used overhead projectors. It's amazing. So we have a couple different curves that we're going to graph. Is this still good with lights off?
Seems good to me, yep.
Okay, so we wanted to graph r equals 3 plus 2 cosine theta. So There are two ways to do this. Well, I guess three if you count just graphing it in your calculator, which I'm not really going to count. So you could just tediously plug in points. Theta equals 0. Cosine of 0 is 1. 1 times 2 is 2. 2 plus 3 is 5. So I have a point. Let's graph that point. So, boom, I have a point. Then I can do it again. When theta equals, let's say, pi over 3. Cosine of pi over 3 equals 1/2. Half of 2 is 1. 1 plus 3 is 4. So at pi over 3, we should get a 4. Maybe? No. Right there. What you hopefully know, or have noticed already, is point plotting is very, very tedious and slow and kind of takes forever. I don't want to just plot points over and over and over again. That's kind of terrible. So what I'm going to use is I'm going to use a graph to help me make another graph. So I know what this function looks like. If this is kind of y and this is x. If this basically said y equals 3 plus 2 cosine x. This is just a cosine graph shifted up 3. So the midline's at 3. Amplitude is 2, so it's stretched up by a factor of 2. No period change, nothing weird here, no phase shift. This is just a quick, easy cosine curve, just stretched vertically by a factor of 2, shifted up 3. If you'd like to rewrite it like this, then by all means do that. So cosine kind of starts at the max, and then it goes down. So it basically just looks like this. My scale is by pi over 2s, which is hopefully obvious. If you're not sure, just check this thing. Cosine of 0 is 1. 1 times 2 is 2. 2 plus 3 is 5. And I kind of just get that point that we were talking about. I can just see it right there, that if this is the theta axis and this is the r axis, when theta is 0, r is just 5. So perfect. And I can also just see this point, that when theta is pi over 2, r is just 3. This is just a display of inputs and outputs. That's all you get when you plug in stuff is inputs and outputs. This is just showing kind of a general trend, though. It doesn't show that pi over 3 4 point because we didn't make our graph super detailed, but that's okay. We can just see that when theta changes from 0 to pi over 2, the r's just get smaller and smaller and smaller and smaller and smaller, which for us that means just plotting on a closer and closer ring. That when theta is like pi over 12, r is slightly smaller, so we'd be only out here at like 4.7 or something. When theta is pi over 6, that r would just be like 4.2. That we can just tell this whole time, as theta gets bigger, r gets smaller. And r getting smaller for us just means we're plotting on sort of closer and closer rings, aka getting closer and closer and closer to the pole. So we should look like this. Did I plot it perfectly? I highly doubt it. Could I make it more accurate if I plotted some more points? Yes, but that's really not the point. We want to get this done relatively quickly and have an idea of what the curve looks like. If we want it better, we can always plot our points, but plotting our points just takes more time. And then I can kind of see here, between pi over 2 and pi, that as theta gets bigger, r just gets smaller and smaller and smaller and smaller and smaller. So that means closer and closer and closer and closer until at pi, we're just 1 unit away. So here we are getting closer and closer and closer. So here this is 1.5 units away, this is 2 units away, this is 2.5 units away, theta's 2.5, 2, 1.5, 1. R just got smaller and smaller and smaller. And then in these sort of third quadrant angles between pi and between pi and 3 pi over 2, r just gets bigger and bigger and bigger and bigger and bigger. And for us that just means further and further and further and further away until we're 3 units away. So here's 3 pi over 2, here's 3 units away, here's us getting bigger. And then the rest of the time, as theta gets bigger for these like fourth quadrant angles, as theta gets bigger, r just gets bigger until you're 5 units away. That's it. Quick and hopefully somewhat easy. Quick little things that I like
That's called a limasan.
Yes. One, this thing is called a limasan, which hopefully you remember. There's this weird little thing under the C that I never remember what it's called.
It's a Frenchy thing.
It's a Frenchy thing. And apparently, I learned this yesterday, limasan, or like on Friday, limasan is French for like snail or something.
Ooh.
But it just looks sort of something like this. I like to add a couple other things to our graph. I like to add arrows. And I'll sort of explain what the deal with the arrows is. The arrows is sort of the flow where the way points are generated. So if I just plotted a point here, and I increase theta, the points would come in this sort of direction. So as theta increases, points just go sort of like this. If I just plotted a point here and it came from some particular theta, if I made theta a little bigger, the next point would sort of be here. You don't have to put arrows all over the place. I maybe even have too many myself, but just a couple should be good enough. The second little thing that really isn't the biggest deal in the world is a lot of people sort of have this problem where they make their things like sharp and pointy. They'll just connect those 2 points sort of like this. Maybe it's not entirely clear why that happens, why we should be making it flatter, like we do, or maybe when you graph these things in pre-calc. But you kind of know that the tangent line here is horizontal. And here, these are the points of inflection on your sines and cosine graphs. So here, you're sort of decreasing slowly. So R should kind of barely be changing at the beginning, up where those maxes and mins are for sine and cosine. A lot of people just make these sort of too sharp and pointy. It's not the biggest deal in the world, but they generally should be flatter here around the maxes and mins of the graph, that there are minimal changes in R happening and more rapid changes happening here.
And if you plot theta equals pi over 3, then you see that your first one.
Yeah. Since we actually plugged in pi over 3, we can sort of tell that that's kind of a bad job. If you want a couple other points to make this look a little better, pi over 3 should be friendly for your cosine graphs, because pi over 3 should be a half or negative a half if you're talking cosine, and your pi over 6s, 7 pi over 6, 5 pi over 6, are 1/2s or negative 1/2s for sine. So if you want a couple extra points to make it look a little better, I would recommend pi over 3s or multiples of pi over 3 for cosine and multiples of pi over 6 for sine. That's pretty much it. This one's a fairly nice example. We're going to run through a couple other sort of weirder ones, but really just not that weird, but slightly harder than that. So the next one I want to do is R equals 1 minus 4 sine theta. And all these problems should be in the packet you got last class when we started talking polar. So no tedious point plotting. It's tedious, it's slow, it's terrible. This is just a sine function shifted up 1, stretched by a factor of 4, and then we've also got this annoying negative, so we also got flipped over. So midline at 1, amp is 1, 2, 3, 4 higher, and 1, 2, 3, 4 lower. Standard period of 2 pi. So let's just graph our sine curve. Sine starts at the midline and increasing, except we've been reflected, so we should be decreasing. So we should look like this. If you're unsure about what the deal with stuff is, just check. Plug in pi over 2. Sine of pi over 2 is 1. 1 times negative 4 is negative 4. So this is 1 minus 4. That's negative 3. That's perfect. So let's just use this to our advantage. So I've got that point. When theta is 0, this is my theta axis. This is my r axis. When theta is 0, r is 1. So boom, point, got 1. And then as theta gets bigger, r just gets smaller until eventually r is 0. And I'm not entirely sure where r actually hits 0. I could find it if I really, really wanted to and just set r equal to 0. And I get like sine of theta is a quarter. So theta is like the arc sine of a quarter, but I don't really know what the arc sine of a quarter is, so that's really just not that helpful to me. I just know as theta gets bigger, r just gets smaller and smaller and smaller until it's 0. Where does that happen? I don't know. Let's say theta hits 0, like right there, right around pi over 12. So let's just make theta get smaller. Or sorry, let's make r get smaller as we increase theta. So we graphed this part, the part where all the r's are positive. What's weird is most of the r's for these first quadrant angles are negative. So like this little chunk, all the r's were positive, and then sort of from here to here, all the r's were negative. So when I have a negative r, I kind of just mirror myself over to the other side. So sort of from here to here, all those angles are going to be mirroring over here. So we've basically got -1, -1.5, -2, -2.5. So here, this point isn't going to plot here at 1.5, it's going to plot over here. And then we're not going to plot here for 2, we're going to plot over here. And then r is going to bump up to like -2.5, and that's going to mirror over here. And then eventually, when theta is pi over 2, r is -3, that's going to move over here. So we're at -1.5, -2, -2.5, -3. There's no -1.5 ring. I'm 1.5 units away on the opposite side. I can't plot on the negative second ring. I plot on the second ring just on the opposite side of where I was supposed to go. So we're going -1, -1.5, -2, -2.5. We're getting further away just on the opposite side. As absolute values, those go 1.5, 2, 2.5, 3. So we should just be getting further and further away just on the opposite side. So we just look like that.
Pi over 6 might be good might be worth plotting.
Yeah, we could plug in pi over 6 if we wanted. Sine of pi over 6 is a half. Half of 4 is 2. 1 minus 2 is going to be 1. So at pi over 6, or sorry, 1 minus 2 is -1. So at pi over 6 here, we should be basically a -1, which I basically am. I'm off by like 0.1 units. But if you want to make it a little more accurate or give yourself a sort of checkpoint, then by all means do it. So then here, the second quadrant has sort of a similar problem. The sort of traditional second quadrant angles have a very, very similar problem. Most of the r's are negative, and then we've got this tiny little bit that's positive. So r in the second quadrant, all these angles, the beginning angles in the second quadrant, all have negative r's. So they're actually not going to graph here. They're going to mirror over and graph in the early part of the fourth quadrant. So here, we're -3, -2.5, -2, -1.5, -1, -0.5. That's getting closer just on the opposite side. So we should just be sort of looping in like this. Until we get here, until eventually r is 0, which happens somewhere. Who cares where? It should be easy to tell that most of the r's should be mirroring over and only a handful of them are sort of staying in the fourth quadrant, or sorry, staying in the second quadrant. So this little bit of second quadrant angles have positive r's, and so r is now 0, and now r is going to get bigger and bigger and bigger until r is 1. And that happens at pi. So here we are getting bigger and bigger and bigger. And now the rest of it should be kind of nice and friendly, similar to the first example, that these third quadrant angles are kind of nicest. Because all the r's are positive. R is 2, 3, 4, 5. You're just getting further and further and further away on the opposite side. So let's give ourselves a sort of guide mark. And then let's just move further and further and further away until r is 5. And then the fourth quadrant angles are also super nice. As theta gets bigger, r just gets smaller and smaller and smaller and smaller, which for us means closer and closer and closer and closer until we're 1 unit away, which actually takes us back to where we started, and we look something like that. I like to add arrows. We started with this thing here, and then we kind of looped in, and as theta got bigger, we sort of came in and made this little loop, and then we increased theta and then did this, and then we sort of just looped ourselves around until we made this. This thing's also called a limacon. It just has a weird little loop. Anything in the form a plus b sine theta or a plus b cosine theta is called a limacon, although some of them have loops, Some of them don't have loops. There's a relationship between A and B that tells you kind of when they do and do not have loops. You hopefully know what that is. Basically the cause for our loop though is the fact that we have first quadrant thetas with negative r's that are mirroring over into the third quadrant, and also third quadrant thetas with positive r's that are creating these larger values in the third quadrant, or these values that are further away. Similar here, we have these negative r's in the second quadrant, but also these positive r's in the fourth quadrant, which are getting us close points and sort of further away points all in the same place. So really the deal with when there is a loop and when there isn't a loop is if this is bigger than this. If your amplitude sort of stretch is bigger than your shift, then you're going to get a mixture of some positive and some negative r's.
If the auxiliary graph crosses the horizontal axis, that's another way of putting it.
Yes, that also works. You can also kind of think about it as in the same way that we think velocity acceleration in terms of speeding up and slowing down. Here, r is positive and then getting smaller. That should be us moving closer to the pole, aka the origin. And then here, r is negative and getting more negative. So we're moving away from the sort of theta axis, we're moving away from the pole. We're -1, -2, -3, that's moving further away on the opposite side. So we're negative and decreasing, that's us moving further away. That's us doing this little loop here. Whereas here we're negative, but the graph is increasing, so r is -3, -2, -1. That's on the third ring, second ring, first ring, that's moving us closer to the pole. Here we're positive and increasing, that's going to move us away from the pole. So that's us doing this. And then here we're positive but decreasing, r is 5, 4, 3, 2, 1. That means closer, 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 closer. And that's pretty much it. If you can get the hang of how to handle the negative r stuff, which is probably the most confusing part about using the auxiliary graph, then they're all the same. You don't have to memorize rules like anything like this is a Lima sum, that if this is smaller than this, then there is a loop, and if this is bigger than this, there is a loop. Wait, what if it's negative? If you can get the hang of the negative r sort of reflection thing, then you're totally fine. Mr. Rose?
It might be helpful to label the polar points. Like that first one is like, I make my class do that. I think it's helpful.
This
like,
point
yeah,
is
in polar coordinates, it's like
0, 1.
Or 1, 0, right?
Yes, 1, 0, and then this point is -3, pi over 2.
Yeah.
And then this point is 1, pi. And then this point is 5, 3 pi over 2.
Yeah.
And then we finish the job getting back here with 1, 2 pi. And that was the finish. That's pretty much it. I just want to take a peek at a couple more extra, or a couple other graphs that kind of have a mix of positive r's and negative r's, but also particularly one where we change the period of our sine graph. So 2 more hopefully quick graphs. The first one is just going to be r, or the 2 on the back of the paper that you already have. We've got an r equals 4 sine theta, and then we're actually going to graph one where we actually change the period.
You have 8 minutes, so if you go fast, you can squeeze them both in.
Okay.
7 minutes.
So actually, let's just skip to the last one then, to be super confident. We will finish this. Let's do 5 sine 2 theta. So at least one where we actually change the period. The period should just be 2 pi divided by 2, or pi. Amplitude is just 5. So if I'm making my auxiliary graph, 5, -5. You don't really need to make individual tick marks here, but the period has been cut in half, so we're going to finish a cycle by the time we get to pi. So here you want to scale by pi over 4s. You really don't need to label every single horizontal tick mark. So sine starts at the middle, and it increases. We get a graph that looks, oops, did I miss one? I did miss one. I just can't count. We get a graph that looks something like this. And if you're not sure, just double check. Pi over 4 doubled is pi over 2. Sine of pi over 2 is 1. 1 times 5 is 5. Perfect. You want numbers half as big here because they're going to get doubled, hence the little squishing or compression horizontally. But if you want the period, just 2 pi divided by this number, and then you're fine. So let's use our graph to our advantage. First quadrant angles are all nice and pretty, from 0 to pi over 2. That's as nice as it could possibly get. All the r's are positive. So we start at 0, or at the pole. And then as theta gets bigger, r just gets bigger and bigger and bigger and bigger and bigger until we get to pi over 4, and that's when r is its biggest at 5. So here, we should just be getting bigger and bigger and bigger and bigger. And then the rest of the first quadrant, the second half of the first quadrant, all the r's are getting smaller and smaller and smaller. So theta is theta gets bigger, and then r is just 4, 3, 2, 1, 0, aka closer and closer and closer. So first quadrant, done. Second quadrant, kind of super annoying, because all the r's are negative. So here at pi over 2, we've sort of started moving this way and made this little loop back. And we're back at the pole now, because when theta was pi over 2, r was 0. And this whole time, r is just -1, -2, -3, -4, -5. We're moving further and further and further away, but on the opposite side. So all these are getting mirrored over. So this thing is a -1, it's getting mirrored over. This thing is like a -3, it's getting mirrored over. This thing's like eventually a -5, it's getting mirrored over here. So we're moving further away, but just on the opposite side, which should just mirror us over here. And then here, the rest of the second quadrant, r is -4, -3, -2, -1, 0. That's closer and closer and closer, but on the opposite side. So we're not plotting here, we're plotting here and then kind of coming back. So if you want to add arrows as you go instead of at the very end, then we have a sort of situation like this. Third quadrant is back to being super nice and friendly. We made it back to the pole again, and as theta gets bigger, r just gets bigger and bigger and bigger and bigger, until by the time we're 3 pi over 4, or sorry, by the time we are 5 pi over 4, r is just 5. So here we are getting bigger and bigger and bigger, and then here we are getting smaller and smaller and smaller until we're at 3 pi over 2, and we just look like this. And then the fourth quadrant is kind of the same situation as the second quadrant. All the fourth quadrant thetas are negative, just like all the second ones. So the second quadrant angles actually graphed into the fourth quadrant, and the fourth quadrant thetas are actually going to mirror themselves over into the second quadrant. We're going to move further away on the opposite side. So now these angles are going to mirror over here instead of the reverse scenario. And we're just going to move further and further and further away. And then these angles here are going to get closer and closer and closer. R is -4, -3, -2, -1. That's code for closer and closer and closer, just on the opposite side. That's it. For vocabulary purpose, this is called a rose. Anything that's in the form of r equals a cosine n theta, or r equals a sine n theta, is a rose, assuming n is an integer, and n isn't 1. Or I guess I should say 0, either. Those things are just called roses, even though maybe that doesn't look like a rose.
Looks like a flower.
It's some form of flower, anyway. So that's how you...
Even though, one thing, even though the equation 5 sine 2 theta, even though that has period pi, you have to actually graph 2, you have to graph through 2 pi in the auxiliary graph to like see the full shape.
Correct.
Yeah.
But if we kept going with this thing,
It'll just repeat.
We're just going to graph itself. We just finished this fourth quadrant loop here, and if we started using bigger angles from say 2 pi to 7 pi over 2.
It's going to do it over again. You have 30 seconds also.
Oh, so 5 pi over 2 I mean.
Yeah.
But we would just make this little loop again, so that's kind of worthless. So that's it. The example we didn't do on the top is a circle, which you should know kind of from the conversion we did at the beginning of this video, but it's probably not bad for you to try that too. Cool. So end of video 1, we're going to do some calculus with our polar in about 5 seconds.
Okay, done.